Welcome, ladies and gentlemen. Let's go ahead and take a look at our Bellwork responses today. So we can tell whether or not an infinite series converges or diverges if it's a particular type of series. We're investigating two in particular. Firstly, I'd ask that you share whether or not the series given in number 1 converges or diverges. So what did you guys say for that one? Carter and Lauren?
Yeah, we said diverges.
Diverges. Raise your hand if you also said diverges for number 1. Keep your hand up if you have a reason. Why would that diverge? Thanks, hands down. Ben H.
It's in arithmetic.
Thank you, Ben. Diverges because all arithmetic sequences, right, diverge. Awesome. The only way for a series to, an infinite series to have the possibility of converging is if the nth term approaches 0, right? In an arithmetic series, the nth term continues to change and doesn't approach 0, right? It continues to change by a set amount. So there's no way that the overall series is going to ever converge if it's an arithmetic one. Awesome. Take a look at the second one. Go ahead and share. Does this series converge or diverge? What did you guys have? Lexi and Evan?
Diverge.
Raise your hand if you have diverge as well. Diverge. And why would this diverge? Sammy?
5/3 is greater than 1, so it diverges the geometric series.
Absolutely. And so this infinite series also diverges. There's not a particular, right? There's not a particular value that the series converges to. It diverges. And again, this was a geometric series with my ratio r equals 5/3, which is greater than 1. Right? Therefore, the sum is going to become infinite, and it diverges as a series. So geometric with my constant ratio r equals 5/3, which is greater than 1, so diverges. Awesome. And yes, lastly, the moment you've all been waiting for, does the final series converge or diverge? Spencer and Ben? Converges. So this series converges. Why does it converge, Matthew?
R is less than 1.
Yeah, in this case, again, geometric series, but my ratio, my constant multiplier, r, this time equals 1/3, which is less than 1, right? So not only do we have the nth term approaching 0, again, repeated multiplication by that 1/3, it's geometric. If my ratio r is less than 1, then this will converge. In fact, we even have a formula that we developed last time to be able to tell what it converges to. So first, before we do the convergence, I'm going to say that this is a geometric series. With my constant multiplier r equals 1/3, which is less than 1. So it converges to, and not only do we know that it converges, we also have our handy formula where the infinite sum is calculable and it converges to, let's see, I want to call this maybe g sub 1 for the first term in a geometric series over 1 minus r, and we'll simply evaluate my formula for the infinite sum. So g sub 1 would be go to the series and evaluate, right, when n equals 1 to get the first term. So n equals 1 is 1/3 times 5 is 5/3. So the first term is not 1/3. The first term is not 5. We still need to evaluate this when n equals 1 to get the first term, and I get 1/3 times 5 is 5/3. So 5/3 is g sub 1 all over 1 minus, and we already saw that r was my 1/3. A little simplification, and we get 5/3 divided by, go gadget arm, 2/3. And we could multiply by the reciprocal, or we could reduce, right? We see those denominators are the same, so my final answer I'm getting is 5/2 or 2.5. Raise your hand if you had 5/2. Anyone else have that? Yes. Oh, great news. Awesome. Thank you. And what questions do you guys have about our Bellwork today? Okay. I'm going to go ahead and pause the recording. If you kindly give yourself credit for those who completed on OTL number 1. Okay, I appreciate your help with that. Let's go ahead and take a little a little trip down memory lane, right? As we have a little quick and dirty refresher for vectors and how we can express both direction, magnitude, and location, right? Position using vectors. And so let's suppose that, as a reminder, we'll put ourselves in one of those little classic ACT type problems. The ship travels at 8.5 knots. Remember, a knot is a nautical mile per hour. For 4 hours at a bearing of 43 degrees. Everyone, let's go ahead and draw a vector indicating the ship's position at the end of 4 hours. We'll then label the vector's magnitude and direction. So a little reminder, right? We can express that a vector is not a scalar quantity. A vector, right, includes both magnitude and direction. So I think back to the original Despicable Me, where it had Victor, right? And he wanted to go, Dad, no, call me Vector. I have both direction and magnitude. Oh yeah. So let's go ahead and express this position again with a vector. So everybody, we can remind ourselves how to do that. It looks like a bearing of 43 degrees. That starts from standard position, right? Pointing what would be in the direction of the positive x-axis and spinning counterclockwise, 43 degrees. And then we'll go ahead and draw our vector. So where would our 43 degrees go? Well, it'll go right here. And how would I express the magnitude? Well, in general, we can kind of say our magnitude is r, right, for resultant when we're talking about in physics, but we could get that by considering our speed in nautical miles per hour times hours would give me knots or nautical miles. So let's see. We were going 8.5 knots per hour. So no, that's knots. For 4 hours. So then, isn't that just that? So I'm getting 32 plus half of course 2, so 34 nautical miles. Okay, so if I go ahead and replace r with our 34 nautical miles, then we've got, have we satisfied the prompt? Let's see. We've drawn a vector. It's indicating the ship's position, so that'll be right here. 34, and we've labeled this and direction. There we go. Okay, everybody good? All right, so we're going to go ahead and take now my nice drawing, and we'll answer questions like, how far to the east is the ship compared to its starting position? All right, so let's go ahead and fill in our picture. It looks to me like we already know my resultant r, which is 34. We had a acute angle measure of 43 degrees, and look at that cute little triangle. Acute little triangle. Can we calculate how far the ship is to the east of its starting position? Well, absolutely. I don't want you guys to think that this is what that little red mark was, part of a right angle symbol. Okay, so how would I calculate that value x? Right. So how would I calculate that value x? What is it that I bless you, Astrid?
You do cosine of 43 degrees equals x over 34.
Absolutely, thank you, Astrid. We've got a right triangle, so we can use all of our SOHCAHTOA ratios. We know cosine is the ratio of adjacent over hypotenuse, and so I'd say cosine of 43 degrees equals adjacent side length x over hypotenuse length 34 nautical miles. And so it looks to me like x is given by magnitude 34 times cosine 43, and this is old news, right? We did SOHCAHTOA, right, depending upon where you first saw it, back in geometry, and then again in advanced algebra or algebra 2. And we'll go ahead and just get approximation. And remember, your default for your graphers is radians. In fact, we work almost exclusively in radians for the AP exam. The exception would be with our projectile motion here, where we give it information in degrees. And so we're going to go ahead and do degrees make sure you change that manually, and then our home screen, we can calculate an approximation, 34 cosine of 43 degrees. So it looks like about, and if we keep our AP 3 decimal places, so that's about 24.866. And what would a label on this be? This would be penguins, dollars, percent. What would our label on this be? Sammy?
Knots.
Yeah, knots. No. Nautical miles, because knots is nautical miles per hour. So knots is a speed. So then this would be nautical miles. So I'll just go ahead and do miles there. So knots isn't a distance, right? It's not a length, it's a speed, I guess, is a way to do it. We need a distance for that. Cool. All right. Go ahead and calculate how far north the ship is from a starting point, then do that with your partner now and be ready to share. If you haven't already, let's go ahead and calculate that. Vertical component. And which trig function are you using this time? Right? Which trig function are you using this time? Sean?
Sine.
Yeah, the sine of acute angle 43 degrees is given by a ratio opposite of our hypotenuse. So it looks like y over 34. So we get y equals 34 times sine of 43 degrees. And that's old news as well. What did you get for your decimal approximation for that? What did you get for that? Ben? M?
23.188.
23.188. Raise your hand if you have the same. Awesome, great, thanks, hands down. We'll go ahead and do nautical miles again. Great. So we've got now a systematic method for determining, right, this kind of vertical leg length in my triangle, and this horizontal leg length in my triangle, and that's where we're after. So the component form of a vector, right? Can we quickly and easily express the horizontal component, comma, followed by the vertical component if we're given the magnitude and direction of a particular vector? Well, absolutely, right? So that's what we're going to generalize today. We know that regardless of our magnitude r and our angle or direction theta, we could calculate this vertical displacement y using the sine function, as we just did with our second example. We could calculate the horizontal component, right? That x distance, that horizontal distance, using the cosine function, and that's just based on a right triangle trig. Now we can summarize our horizontal versus vertical component and get rid of those question marks from the last slide. So we know in general that the cosine of theta is given by x over r. Rearranging this for the horizontal component in my vector form is simply x equals what? How would that look rearranged? Lauren?
R cosine of theta.
Absolutely, thank you. Similarly, rearranging our right triangle subtotal back from geometry, where the sine of theta is opposite side length over hypotenuse side length. We can rearrange that and generate our vertical component. Our vertical leg length is given by y equals what, Isabella?
R of sine of theta, or m sine of theta.
Absolutely, r times sine of theta, and that's what we can fill in our component form. So in general, given the magnitude r and direction, right, direction angle theta, we can get the horizontal component of the vector, where we write these special little vector brackets, kind of like an ordered pair, but not an ordered pair. The horizontal component then is given by r cosine theta. Oh gosh, I'm trying so hard not to work any pirate jokes, but it's been difficult. And my vertical component is given by r sine theta. Thanks, Evan. That was touching. All right, so can I go backwards? Well, if I know the horizontal component x and the vertical component y, what formula relates x, y, and the magnitude, r in this case. Oh gosh, well, that seems classic, right? What formula relates x, y, and r? Brandon?
The square root of, oh wait, do you want,
We
R
get-
squared, R equals, or
You can go right there.
R equals the square root of x squared plus y squared.
Awesome, thank you. This horizontal leg length x, right? That's a leg of a right triangle. Y is the other leg, and so we know the Pythagorean theorem relates x, y, and r. From x squared plus y squared equals r squared. Furthermore, we know that because we're dealing with a magnitude, that's always positive, so we don't need to include the plus and minus. Thank you, Brandon. Direction. How would I go and figure out direction if I'm not given theta, right? What relates my side lengths x, y, and r? Too tough to tame. Ben H?
Would it be tangent inverse of y over x?
Ooh. I'm loving it. And so we know that we've got all 6 trig functions could be written to relate that acute angle theta in that right triangle. But if we have the horizontal component, x, and the vertical component, y, then the quickest way would be to rearrange our tangent function, which depends solely on x and y. Then, I mean, they both have r's in them, so it will reduce anyhow. If we said the tangent of theta equals y over x, then rearranging that to give us our patent pending, truth to you arrow, would give us theta as the inverse tangent. Thanks, Ben. Want you on my team. As do I want Ben and Ben. Oh. Yeah, we could have Ben cubed. We could have a Ben party. Have you been there? That'd be sweet. Alright, so theta equals the inverse tangent of y over x. Now, this is great, except for one problem. What kind of outputs is this inverse tangent function going to give us? What kind of outputs is that inverse tangent going to give us? Kurt? What?
Just like that angle.
It's going to give us the angle, right? It's going to give us angles, but it could give us angles like, 17 degrees. It could give us angles like 49 degrees. It could give us angles like 84 degrees, right? Is it going to give us angles like 112 degrees? No. Is it going to give us angles like negative 37 degrees? Yes, it'll give us negative 37, right? But it's only going to give us angles in between negative 90 degrees and positive 90 degrees because our calculator is programmed, right, only to spit out inverse tangent outputs that are in between negative 90 degrees and positive 90 degrees. That was from our inverse trig refresher. We know that we restricted the original domain to include one disco of the tangent function in order to generate the inverse tangent, right? In your particular rose compass, are the only angles we're going to experience for bearing in between negative 90 and positive 90? No. So what do we have to do? Well, this just gives us the acute angle in reference to the horizontal. We would have to purposefully add or subtract that from the nearest horizontal, right, based on the particular quadrant in which the vector, the terminal side of the vector, lies. So you have to not only do the inverse tangent of, right, y over x, we then have to adjust to fit the given quadrant. So I'm going to go ahead and do that with a quadrant all caps. And we'll see what. So this will give us an acute angle, but we know full well that some bearings might be 213 degrees. So what would we do? We'd have to take our inverse tangent value and add or subtract it from the nearest horizontal, such that we land in the given, that we land in the quadrant that the original vector is pointing. Sweet. All right. So let's go ahead and practice a couple. Then we'll have our closure, and then you'll have a chance to check out our projectile motion activity. So first things first, can we write the described vector in component form? You bet your boots. Right? We know that our component form, bless you, is horizontal component followed by vertical component. And we know in general, my horizontal component, right, my horizontal component is x equals, and what is x given by? Right, what is x given by with r's and thetas? Evan?
R cosine theta.
Great. So for us, we could calculate our horizontal component simply by taking our magnitude, R, 13, a direction angle of 80 degrees, and just do cosine of 80 degrees. No problem. That's easy cheesy. That's easy. Again, make sure you're in degree mode. Similarly, we know our y, our vertical component, is simply given by r sine of theta. And I'm going to call on you for the decimal approximation correct to 3 places, so be ready. So what do you get for that horizontal component, Lauren?
For x.
Yep.
2.257.
2.257 correct to 3. Raise your hand if you have the same. 2.257. And the vertical, Lexi?
12.803.
Gosh, there's a big discrepancy between 2.257 and 12.83. Is that right? Well, think about our direction 80 degrees, right? Our direction 80 degrees is close to 90 degrees, and so we're talking about a tall vector where it makes sense that our horizontal component wouldn't be stretched very far. I got 3 of them. Ben.
Sorry.
Okay, so this is certainly reasonable because our vector direction is 80 degrees, and so we know that this is going to have a smaller horizontal component than it does vertical. So certainly that seems reasonable. Nice job. All right, magnitude of 34, direction of 215. Now we'll be able to take care of our different quadrants other than 1 or 2. Let's go ahead and see what that looks like. I'm getting negative horizontal and vertical components. Are you guys getting negatives? What's going on here? Is it okay to get a negative horizontal component? Ben H?
I would assume yes, because if you didn't include negatives, you wouldn't be able to tell what the direction was from the 2 components.
Absolutely. If we spin 215 degrees from standard position, right, we're talking about ending up over here, aren't we? Quadrant 3, where I'd expect, right, to end up to the left of my starting position and down, denoted by the negatives, so no worries. Nice job. Negative 27.851 and negative 19.502. And raise your hand if you have the same. Did you guys get those already? Hey, that's easy cheesy. Can we go the other direction? Gosh, I hope so. State the magnitude and direction of the given vector. Oh, 815. So now we're given the horizontal and vertical component. We have a vector stated in component form. Well, that's easy cheesy. We can get our magnitude r. Brandon already told us the formula for that. And we can get our direction theta. What formula are I used for r generalized without numbers? Matthew?
Square root x squared.
Awesome. Now we can get specific. We know that that will be given by the square root of 8 squared plus 15 squared. Those numbers ring a bell, isn't that a triple? 8, 15, 7. So let's see. 64 plus 225, 289, root 289. Oh yeah, so that works out nicely. So I'm getting 17. Are you guys getting 17 for the magnitude? 17? Yes! Great. And our direction is given by inverse tangent of, but then I have to determine quadrant. So we'll go inverse tangent of y over x. In this case, that's the inverse tangent of 15/8. Is that right? Inverse tangent of 15/8. And inverse tangent of 15/8. Don't know what that is. 61.928. What's that? Which quadrant is that in? Yeah. 61. So that's just in quadrant 1, which makes sense because we're to the right and we're up. Hey, that's no problem. Raise your hand if you're able to produce at 61.9 degrees. You guys get that? Awesome. And 1 to go. So state the magnitude and direction. Be ready to share. Do it. Do it. Okay, go ahead and share. Did you get the exact form for magnitude R? What did you get for R, Kurt?
Square root of 74.
Raise your hand if you had a square root of 74 for the exact. Good. And we can change that to a decimal just to see about. I like the exact. That's why I call on Kurt. What was that as a decimal, Ben M?
8.602.
Awesome. Thank you. And what did you get for your direction, your theta direction? Well, in order to get that, right, we went ahead and did our inverse tangent of y coordinate over x coordinate. I'm sorry, vertical component over horizontal component. And that put us with a negative input. No problem. Inverse tangent can handle, right, can handle any input, right? The thing is, it's going to spit out inputs that are in between negative 90 and positive 90 degrees. I don't think that's a problem for us. In which quadrant does the original vector lie? In which quadrant does the original vector lie? Mason? Quadrant 4. And this angle, right, is going to lie where? Well, what do you guys get for that angle? Or
Negative 54.462.
negative 54.462. Awesome. Degrees, sorry, degrees. That's great. Remember that we typically state direction, however, as a positive angle measure starting at 0 and spinning in the counterclockwise direction, right? And so we're not going to put this as our final answer, though correct. What will we put instead? Well, we do 360, right? 360 plus this negative 54, which would put us in quadrant 4. And where would that be then? So for us, we're going to place that purposely in the quadrant using a positive degree measure. Okay, 360 minus that. And so what are you guys getting for that? Did you do that, Sammy?
305.53 degrees.
538. Very nice. Very nice. And that would be the preferred. That would be the preferred direction, right? Just to match like our vector problems when they give us a bearing. Awesome. Great work, you guys. So that was thus concludes our quick and dirty vector refresher so that you guys can jump into our projectile motion activity. So let's go ahead and close it up for the day. A vector with magnitude r and direction theta has horizontal and vertical components given by, and I don't think we need to do time for the right. Be ready because I'm going to call on you. What would x be given by? What would x be given by? Carter?
R cosine theta.
r cosine theta. Thank you. What would y be given by, Astrid?
Sine theta.
Awesome, thank you. How does one find the magnitude and direction of the general vector in component form using a and b? So how would we get the magnitude using the components a and b as it's written? What would that be given by? Isabella?
The magnitude equals the square root of a squared plus b squared.
Awesome, thank you. And lastly, how would we get the direction? Right? How would we get the direction of that? Sean?
Tangent inverse of the over.
Awesome. With the important, right, addition of going to the quadrant, right, to the quadrant based on the signs of the original component. So we'll do inverse tangent of b over a, followed by, comma, and then adjust for the quadrant. Again, I'll denote that by an all caps quadrant, exclamation point. Can't miss that, especially if I use the red color. It really pops. What questions do you have about our quick and dirty vector refresher? Victory. Ben? Hey, lots of space for that too. We're going to go ahead and investigate projectile motion, and that's going to be the context for our introduction to parametric equations. Stamped eligible items include 1C, 4D, 5B, 7, and then one on the extra handout, graph, when you're finished. Then we're going to go ahead and use that final graph as a springboard for Friday's class period. Again, Friday's a little bit shortened, but we've got an important parametric equations activity planned for Friday as well, so I'm very excited about that. Okay, so what questions do you guys have about our discussion thus far? I'm going to go ahead and stop the recording and upload it to our Moodle site. You can scoot into your cooperative learning groups and get started, and then I'll be around to answer questions and issue stamps. Nice job.